residential customers. The primary focus of these field studies was to look at newer HVAC technologies and how they perform in actual homes, kind of coincident with the grid's winter peak. And then, yeah, I guess sort of as shown on this slide too, not only, so then with newer technology, newer heating and HVAC systems, new heating systems that are out in the marketplace, I guess, yeah, in particular, the ones that are electric based, so all electric systems, there's particular interest as it relates to energy efficiency, as it relates to cost effective utility bills, as it relates to wintertime performance, is are these systems, do these systems need or do they use supplemental electric strip heat in addition to their refrigerant vapor compression based electric system? And so as we see, let's see, yeah, as we see here, kind of there's a spike here in the orange example graph. So the orange is the supplemental strip heat and kWh that can spike in the cold winters. And so there are systems that we'll get into here that do have supplemental strip heat, and then there are systems, many systems that do not have or do not need to have supplemental strip heat. And so we'll see kind of like what's their footprint or what's their field performance coincident with the utility peak. So I think kind of in this orange box, I think again, so the primary desired outcome is heavy focus on the KW, the instant demand of these systems, also kind of the average KWH, or the average KW over an hour, or the KWH of these systems throughout the year, and in particular in the wintertime. But also, I mean, we have cooling demands in the Asheville area, and so what's the performance during the summertime from an energy standpoint? And then finally, many of these technologies that we're testing out are what I would call variable capacity, variable speed, variable scroll, variable capacity in terms of the heating and cooling outputs. And so because these systems can ramp up and ramp down based on the sensible load, how is the performance from a comfort standpoint, or from a dew point, or indoor dew point, indoor relative humidity, from a comfort standpoint, from the user perspective, to see how can we sort of scale up this technology, and are there sort of win-win-win situations for the occupant and customers? Is there a win for the utility? Is there a win for the HVAC contractors installing more of these, and the manufacturers as well? So I think kind of getting into some text heavy, maybe one or two text heavy slides, and then we'll get into some visuals here. But I think kind of overall, and so this is called interim findings because this is a smash between the existing home study, which will be first in sort of the slide deck, and then the second part of the slide deck will be reserved for some new home study results. And so I would say the existing homes findings, which will be the first half of the slide deck, is final and complete, 2 years worth of complete data. But this is sort of a summary slide of the existing homes, and then the new homes, which will be the second half, which is still in the interim stage. But from an energy performance standpoint, and from kind of an average power consumption standpoint, I mean, these variable capacity systems, not only on paper are they encouraging and impressive, but then also from what we've measured in the field, we see here that their performance kind of on average is at and below 3.5 kW from a maximum demand over an hour. And then an interesting note, and we can certainly get into this. So we have a sample set of 3 homes in the existing home cohort. We have a sample set of 4 homes in the new homes cohort. And interestingly enough, sort of point number two is that all of the HVAC systems, their winter peak demands of the HVAC system itself did not match the utilities coincident peak of 7 a.m. and 8 a.m. So I thought that was pretty interesting and wanted to share that. Potentially an influence on that, number 3, a potential influence on the performance of the systems of not only like a 30-year-old system, but also a brand new system, a 1-year-old system, is that we had some, in particular, some of the existing homes study participants like the temperature cold pretty much during the wintertime, just in general, and even at night in the wintertime, they liked it in the 60s. So I think that certainly had an impact, especially on the 30-year-old system of lower energy demands, lower energy consumption with lower set points in the wintertime. And then the 4th point is, I think it's still important, is with single speeds, what I would call single speed systems, sort of standard efficiency single speed systems, or 2-speed or multi-speed systems, in addition to the new variable speed, variable capacity systems. I think heat pump, like sizing these systems, is still important and is still critical to maximize and optimize the system efficiency, as well as the moisture management in the shoulder seasons or in the spring and the fall. So I think system sizing and system selection is still important, even though we have the variable capacity functionality. It's still not, I guess, kind of a silver bullet, or it's still not it's still important. So yeah, I think we can kind of, I'll be getting into some of the specifics. So we have a range of efficiencies, but there's some more technical details based on some feedback from some of the committee last month. I've provided some slides on more technical specs that we can get into here. And so, yeah, so which is, here we go. So let me, oh, sorry, I can provide slides. And so I guess if this top bar is in the way, then I apologize, but I'll just kind of keep moving forward. So again, so this is an existing study home group. And so here we have, just a independent unique identifier of the study homes. So 3 study homes. We have one that's called the Beaver Home study home, one that's called the Black Bear, and one that's called the Copperhead. And so the Beaver study home is basically the baseline home with a 10 SEER 6.8 HSPF, older system, probably 18, 19 years old. And so here's some specs on it. What's covered up here, at least on my screen, is this chart is the supplemental strip heat. So this system has 7.5 kW of supplemental strip heat in the air handler that'll kick in when it needs to. And so, and then the next study home, which I would call kind of the intervention, because the Beaver study home is a townhome right next to the Black Bear study home townhome. And so basically the footprint is really similar. The layout is similar. The duct location is very similar. But in this case, the Black Bear has a newer, higher efficiency, centrally ducted heat pump, a Mitsubishi system. And so here we're getting into, so there'll be some various specs that I'm providing. And so here, sometimes the manufacturer will have certain specs and different test parameters or standards or targets. And then we also have some AHRI directory data that has other sort of specs and standards at different test parameters or test metrics. So, but in a sense, we have, a 2-ton system that is the Beaver has a 2-ton system. The Black Bear has a 2.5-ton capacity system. And then the Copperhead was generously, Amy and Vandermuster Design generously contributed their home office to the study. And so there's a geothermal system. It's a 2-ton 18 EER specs there that was also sort of part of this existing home study cohort. Also, some getting into some specs here, we have some duct location. We have some air handler location. We have some duct location. We have the supply registers, our location of the supply registers in the different study homes. We also have the return grills as well located here, and the number of floors, if we need to sort of reference that or sort of come back to those details. But I'd say, I mean, at this point, kind of, we're kind of comparing apples to oranges to maybe pizza, with some of there's a lot of variety in terms of the home conditions. There's a lot of variety in terms of the occupant behavior, and so. But again, overall, I think kind of very, very valuable data. I think in this slide, one of the things that I'm a very visual person, and the main takeaway that I wanted to just have for this slide is that in particular, again, the intervention home. So this is again still the existing homes, a visual of the existing home makeup systems. And so again, the intervention home has a Mitsubishi system, and this is quite a unique system where the air handler is shown here. This is a picture of the actual air handler in the vented crawl space. And so it is a full size conventional air handler that has been connected to the existing duct system. So and then the outdoor unit is more kind of indicative or common of a sort of a mini split type system, where the outdoor unit is sort of more representation of that mini split system, but the indoor air handler is very much Mitsubishi is their whole home centrally ducted standard kind of air handler. So yeah, kind of getting into then kind of maybe some of the exciting data that maybe many of us have been waiting for. So this is the average. So this is the average KW over an hour, coincident with the utility peak of 7 a.m. and 8 a.m. And so the specific, the performance of each of the systems. And so again, we have the Black Bear sort of home is in blue. We have, the Black Bear home is in orange, but the Beaver is in blue. The Black Bear is in orange, and then the Copperhead study home is in gray. And so again, kind of, we see that the average coincident with the utility peak is kind of roughly below that 3.5 kW threshold. There a few dots sort of a little bit above that, but for the most part. And then on the x-axis, we have the outside air temperature in degrees Fahrenheit. So again, one of the things that I wanted to overlay to, hopefully it's not too busy of a slide, but I wanted to provide again sort of a significant context, at least in my opinion, is what are the indoor temperatures again during the winter time. And so these are from our data loggers and from our sensors. And so we can see here that the Beaver study home indoor temperatures in the wintertime were roughly between 60 degrees and 65 degrees. The Black Bear between 57 and 66, and the Copperhead between 69 and 74. And so again, so for me, again, the Beaver study home has a like an 18-year-old 10-SEER system, and so I was expecting it to perform the blue to have a lot more spikes, the blue to run strip heat, supplemental strip heat a lot more, especially when it got colder. And so so I think again, based on the occupant behavior of these low set point temperatures, especially in the wintertime, I think that the supplemental strip heat did not run as much as it may have with other occupant settings. So this slide is showing what is the maximum of each system. What's the maximum KW over an hour of each system per month. And so this is not including, this is not overlapping or overlaid with the utility coincident peak. This is just like over the study, over 2 years of study, duration, what is the maximum kW over an hour of each system for each month. And so I think, yeah, so then this is pretty, I think, valuable information, again, in terms of what's the maximum behavior, what's the maximum footprint of the different systems. I'll go ahead and sort of forward to this slide, because it's all-inclusive slide, and then I've also overlaid another sort of lab test results. So in this case, I've overlaid the Mitsubishi's, the manufactured expanded performance data for, again, the Black Bear home has the Mitsubishi system, the newer Mitsubishi system. And so based on the system specs, I've overlaid the as measured performance in the bars with the orange arrows here to the left based on lab test results at specific lab test outdoor air temperatures here indicated on the far left. And so again, I think the intent of this slide is to say, like, okay, well, how is this Mitsubishi system in the Black Bear study home, how is it performing compared to the lab test results? And so again, here we have sort of so this is 5 degrees Fahrenheit. So 5 degrees Fahrenheit is sort of the highest lab test results. And then we have 14 degrees is sort of less energy demand. Then 23 degrees, 32 degrees. Here, I think, is an interesting detail, and I've included a screenshot of the expanded performance data in the next slide if we want to look at it. But here, based on the lab results, this system is most efficient at 41 degrees outdoor temperature and not 50 degrees outdoor temperature. And so the order of this the side data is actually correct. I didn't mistranscribe. And so the system is actually the most efficient in lab test results at 41 degrees and is less efficient at 50 degrees. And so as we see here, yes, there's a time in November of 2019 in this brown bar where the field results, the data that we measured of the system in November is actually higher than the lab test results. But other than that, I think kind of the lab arrows or the orange rows from the lab data compared to the field data is pretty favorable to what we saw in the field. Yeah, and so if need be, or in the attached slides that we'll be sharing, here's just kind of a copy of a snapshot of the expanded performance data. So if in this conversation it'd be useful for us to revisit this, we can, or in future purposes we can sort of look at that data. But this is sort of what I pulled, a copy of what I pulled. So again, I apologize for the sort of cutting off at the top. I guess let me pause here because it looks like there may be some chats. Okay, so I guess the top bar is only on the prisoners. Okay, so great. So it doesn't seem to be.
Yeah, we're good on how we see it, Jonathan.
Okay, perfect. So we'll keep great. So that previous slide was related to the winter sort of performance and the winter consumption. And this slide is specifically focused on the summer performance. And again, we'll do sort of the similar progression of slides where this is a slide of the data that we measured of the summer, the performance of the cooling system, the air conditioning system, the KW, the average KW over an hour, again, coincident with the utility peak in the summertime. So this is hours ending in 4, 5, and 6 p.m. And so again, I think, and then similar kind of, I think, logic or context. We've provided the indoor temperatures, the summer indoor temperatures as well, to kind of overlay. And again, there's some study homes that tend to like it maybe a little bit colder year round, colder in the summertime than maybe other homes. But again, here is the performance broken out into study home, coincident with the utility peak. And so then here, here overlaid, again, sort of the Black Bear study home, the Mitsubishi system, overlaid it with the lab test results. So from the Mitsubishi lab test, at 86 degrees outdoor dry bulb temperature, the Mitsubishi system was a little bit over 2 kW of consumption of demand. And then at 95-degree outdoor temperature, that same Mitsubishi system was a little bit more than 2.25 kW over an hour under those same test conditions. And so again, wanted to sort of overlay this, our as measured sort of in situ field performance of the different study homes compared to the lab test results from Mitsubishi. So then shifting gears a little bit to, again, to maybe more of the comfort side of the study design. Again, we wanted to monitor and measure and get some feedback on from a comfort standpoint as it relates to relative humidity. So for example, like the 2015 ASHRAE Handbook of Fundamentals recommends that roughly like a 55-degree dew point temperature for the indoor conditions for comfort. And so if we were to then kind of convert that to relative humidity for this chart, that would be roughly 73 degrees Fahrenheit at 53% relative humidity. And so that ASHRAE sort of standard and recommendation is indicated here on this chart in red, the red arrow. And then this orange arrow here is to represent the manufactured, again, Mitsubishi's manufactured expanded performance data of how the system is supposed to perform at certain lab test conditions. And so in that case, so we have that sort of indicated here, about 58% relative humidity at an indoor air temperature dry bulb of 72 degrees Fahrenheit. And then, so then that's then compared to the squiggly line, which is the as measured relative humidity of the different study homes based on different outdoor air temperatures and degrees Fahrenheit there. And so, so as we can see here, there are parts of the year where, and I guess primarily like colder times in the year, where the indoor relative humidity is in agreement with or is below the ASHRAE recommendation. And then there are other parts of the year, like kind of primarily warmer times of the year, when the indoor relative humidity conditions are above the recommended ASHRAE recommendation of indoor relative humidity. So, so that's kind of, I think, kind of from a performance standpoint, what we found. And then I would kind of add sort of, I guess, qualitatively or anecdotally, when I was going and downloading the data and interacting with the participants, and I was engaging with them on just kind of like to confirm what are their set point temperatures, what's their experience been in the study, what's their experience been with the HVAC system, and to just kind of confirm or gather just kind of qualitative anecdotal information. And at no point in the study did I hear any of the study participants say that they felt that their home was too humid, or that it was cold and clammy, or that it was uncomfortable. But I think from my perspective, I would have liked to have had more sort of compliance or lower relative humidity conditions year round, just for me from a study standpoint. And so we have had ongoing conversations for a while with Mitsubishi HVAC. And so we continue to provide them with feedback on the higher relative humidity readings that we've been seeing and measuring in study homes. And so trying to help benefit and influence the manufacturers lower these targets through algorithms or through software settings. Again, sort of if need be, I've provided some cooling expanded performance data, again, based on the air handler models and based on the outdoor unit model numbers and the different test conditions that manufacturer had. So for future conversations or for reference offline. So I think I can sort of transition to the new home studies, and so there's I think that's a pretty good summary. There are a couple of sort of last minute takeaway teasers at the end of the slide deck about that relate to the existing homes, but I don't know. I'm happy to take questions and comments related to the existing homes findings now, or just go ahead and continue on through the new homes interim findings and entertain and then answer questions and comments after that. Does anybody have a preference? Okay.
Yeah, I do not. Probably just let's tie these new ones in, Jonathan.
Okay, great.
Comments to it. Yeah.
So again, as a sort of a quick refresher for some folks, the 4 new homes in the study are quite efficient homes. They're built by the same builder. They have the same subcontractors. The same HVAC contractor did the installs. Again, Vandermusser Design did the Energy Star certification and green building certification. So these are commissioned homes to verify the quality of the installation. And so I think in terms of like the quality of this data set, I would say is much more robust, because these homes are more similar between the homes than the existing home sample set. But again, and so we have roughly sort of 2- and 3-story homes. We also have quite efficient sort of 17 SEER, 18 SEER systems with sort of corresponding 10 HSPF heating season performance of the heat pumps. I would also add that these heat pumps none of these heat pumps have supplemental strip heat. So all of these systems are hyperheat. All of these systems are heat pump only. And we'll see that in their very strong performance. Again, so I think this is again a very busy slide, and wanting to be thorough and provide transparent with the different model numbers and the efficiency ratings. I think the biggest takeaway that I want to, I guess, have right now for the group is that these systems. So yeah, a load an ACA manual J load calculation was performed on all 4 of these study homes. And one of the things that's unique, I think, to this study and to these HVAC systems is that we purposefully chose to and installed heat pumps that were sized to the heating load of all of these homes and not to the cooling load of these homes. And so again, because these are variable capacity systems, we had very high confidence that we could size these to the heating load, and then to minimize supplemental strip heat or eliminate any supplemental strip heat, and then also to be able to ramp down to the cooling load or the heat loss the heat gain of the homes or the cooling load of the homes based on the equipment selected.
So can I ask right here, can you just clarify, is it the BOVA, that's the variable speed conventional technology, and the other is the VRF?
Yeah, so I guess from a terminology standpoint, yeah, so thanks for your question. So I reserve VRF to commercial systems. And so I'm under the impression that like Daikin has uses the term VRF or variable refrigerant flow for commercial grade systems. And so, but yeah, and so I would say that all of these systems, so the Mitsubishi, each Mitsubishi system and each Bosch system is a variable speed and variable scroll, variable demand, variable capacity. And so none of these systems, so one of the features that I'm aware of with a VRF system is that, well, yeah, so that's the terminology that I guess that I've used in this technology. Did that answer your question?
Yes, I had thought that Amy originally said that one of these was not a variable, completely variable speed scroll, but it was some kind of an incremental.
Rick, I'm pretty sure that the Bosch, I'm pretty sure those are either a 4 or a 5 speed rather than a continuous.
Well, we don't need to hold it up, but obviously this is something that I'm going to want to go look at the detail on, because that was one of the fundamental aspects of it, that they supposedly cost less, but that's okay. This is good.
Yeah, great. Yeah, and so they're, yeah, so their model numbers here, and I'm happy to provide additional details. Yeah, so again, kind of the same format. So again, this is the new homes interim study. So we're crunching the latest information now to get 2 years worth of data, but here's the interim data. And again, this is, so the new homes average KW in the wintertime coincident with the utility peak. Very strong performance, very sort of, also sort of in similar theme, the indoor temperatures for each of the study homes is included here on the right of the slide. And then again, so broader than just the utility peak, again, sort of this is the interim findings for each of the study homes, the maximum KW over an hour per month. Up until the latest analysis. So we'll be coming out with some new data here, but so here's again kind of the profile, and so again, roughly for conversation's sake, the Heron study home and the Marmot study home have Mitsubishi systems, and then the Mouse study home and then the Red Fox study home have Bosch heat pump systems, and so that may be useful if you want to kind of cluster them by similar heat pump systems and brands. And so I ran out of time, but I wanted to go ahead and sort of include kind of a similar analysis for one of the multi-head Mitsubishi systems. So kind of like I did with the existing homes, like what is the lab-based expanded performance data for a Mitsubishi, one of the Mitsubishi systems, and during different outdoor temperatures in the wintertime again, compared to our field results. And so here again, just wanted to kind of quickly share that again, this is a Mitsubishi multi-head heat pump. And so the lab-based KW over an hour at 47 degrees outdoor air temperature is about 2.25, I think it was, and then the system performance at 17 degrees Fahrenheit outdoor air temperature is I think about 4.25. And so again, from the field performance that we measured compared to by month, compared to the lab test results and test conditions, look kind of within the range that we were hoping. again, just for the Mitsubishi system, here's kind of some screenshots of expanded performance data that again could be maybe useful in terms of comparison and future sort of conversations. But then sort of shifting over to the summertime, I think again, very, very favorable conditions in terms of low utility bills, low kW demand. We have still kind of a little bit of a variety of the indoor temperatures based on the occupant's preference, but very, very kind of good alignment. And again, the Heron study home and the Marmot study home are both sort of a Mitsubishi heat pump, and then the Mouse and Red Fox are each Bosch systems. So I haven't necessarily made a correlation or if one system is necessarily more efficient than the other, but I think that there's just wanted to point that out with these, I guess, kind of 4 sample sets. And then, yeah, and so then again, the Marmot, sort of the orange Marmot, again, summertime performance, average kW over an hour. So here, the manufactured performance data at 80 degrees indoor temperature and 95 degrees outdoor temperature is the lab test results are kind of, yeah, maybe 2.6, a little bit over 2.5 kW. And so there weren't any conditions as shown sort of on the slide. There weren't any conditions where the Marmot home, the indoor temperature was 80 degrees or even above 73 degrees. But we see here that, again, the performance of this, the as measured performance of the Marmot Mitsubishi system was very much below the lab test results. Again, similarly, don't have to necessarily go into the explanation of kind of the logic of the slide, but sort of similar performance and similar comparison of the ASHRAE recommendation compared to the, again, just the Mitsubishi. Yeah, I apologize. So again, so the Marmot on this slide, I apologize, is blue. And so the orange line is intended to compare the metric to the blue dynamic RH line. And there again, we see kind of cooler periods in the year where the indoor relative humidity conditions are kind of meet or exceed the ASHRAE recommendations below sort of that threshold, the red line. And then they're in warmer times of the year where the indoor relative humidity conditions that we measured were above the recommended ASHRAE conditions. And so for me, yeah, the takeaway is that, and the feedback again that we are continuing to provide to the HVAC manufacturers is that we would like to see more humidity control, more indoor moisture management of the variable capacity systems in the field than what we're seeing and what we're measuring.
Jonathan, real quick, what's the x-axis here? It's like partly cut off in my display.
Yeah,
is that outdoor temperature?
And Fahrenheit, yes.
Okay. So at what outdoor temperature roughly is it going above your lines?
So 58 degrees.
Huh. Okay.
60 degrees-ish.
Yeah.
So none of these thermostats are humidity controlling, specifically humidity controlling on cooling.
That's correct.
Yeah.
It's just sensible, correct. And yeah, and so again, it's been great. I appreciate the opportunity to present to y'all before, and I think that there's great dialogue in terms of like this is kind of like maybe one phase or kind of lessons learned, and we certainly have come up with a lot of questions and hopes of a follow-up study. But yeah, and so that's certainly one wish list item to have for a future study is to integrate in a humidistat into future study designs and systems.
Jonathan, a question on this slide. These heat pumps presumably come with a system setting of either heat, cool, or auto. And so do you know if these were all on the auto setting or, because I find the auto setting to be vexing in terms of energy consumption. If it's got the same setting, temperature set point for heating as for cooling. Is that the case here?
Right. So to the best of my knowledge, like when I visited the homes, they were, when I visited the homes, they were always on either cooling or heating. And so I never saw them, the thermostat set to auto. And then also the fan setting, I was also very, I guess, kind of reinforcing or highly recommending that they leave the fan setting to auto instead of on, to let the system cycle and to let the air handler in particular stop. I would add too that so the mouse house, the mouse study house, one of the I guess the first time that I visited the mouse study house, that system has a centrally ducted Bosch system that has 2 zones, and the air handler is located in the crawl space, and so then it ducts the upstairs system through an interior wall, and so there are 2 thermostats, 2 zones. And the first visit, again at that mouse study house, the occupant was frustrated because the fan for the system never turned off. And so we did some incremental education on and realized that a guest had come in and gone to the upstairs system and changed the thermostat unbeknownst to the tenant. And so the thermostats were set differently. And so in particular, the upstairs system was set, the fan was set to on, but the downstairs thermostat was set to auto. And so there was some incremental education there that we sort of made an adjustment for. And then I would then also use this opportunity to say that the Heron study home, I don't know if people were able to sort of see the technical specs on that slide, but the Heron study home, in my opinion, is the most complicated, is the most unique package, is the unique system of this whole study, where the Heron study home has 1, 2, 3, 4, 5 indoor heads with 1 outdoor unit, Mitsubishi system. And so the owner of that home and occupants of that home, they had a bit of a steep learning curve trying to understand and decipher the remote control for each of those 5 heads. And so I think just kind of, from a study design, from a lesson learned standpoint, I would highly recommend that, especially with these newer systems, to have some sort of like occupant orientation on how to maximize the system functionality or how to explain the different settings for the occupants.
Yeah, it sounds like it.
Is this, I'm sorry, go ahead.
So then I think here's sort of transitioning a slide that I think we had some questions and some curiosity at Advanced Energy because we were seeing some high energy use kind of in outliers and outlying conditions. And so we ran the data specifically to say, like, okay, if we were to take the maximum winter KW over an hour per month, and we were to filter it to the 98th percentile, and then scrub out like 2% of the time, we have some really high energy users. And then 98% of the time, it's quite low, that these systems, the demand of these systems. And so the intent of this slide, and so this is the existing home cohort, and then we have the next slide is the new homes cohort. But here is okay, if we were to have a thermostat program, or if we were to have another sort of behavior-based intervention or program to really scrub out or really try to eliminate 2% of the high energy using demand of the participating systems, what does 98th percentile look like compared to 100% of the field data? And so these green arrows above each study home location is meant to sort of capture the maximum. So in this case, the Beaver the Beaver study home maxed out 100% of the data of one of the months, maxed out a little bit about 4 and maybe 4 1/3 kW. And but then 98% of the time, the Beaver home was much lower than that. And then likewise, the Black Bear. So that's these green lines above each of the study homes is to try to represent 100% of the data compared to 98% of the data that is much lower by month. And again, in the different colored bars. Existing homes here, and then the new homes here. And so again, kind of potentially for future studies or future lessons learned, it's like, wow, like this is even more savings if we were to able to knock down the 2% of the high energy using times. If we were able to knock those down, then we could get even more favorable results and energy savings for the occupant, comfort savings. So yeah, so I think again, kind of a lot of positive results to verify that yes, in fact, the systems on paper or the way that the manufactured expanded performance lab test data and the AHRI test data, it did in fact was fairly close and favorable to the field, the in situ field results that we measured in these study homes. And again, sort of sample set of 3 homes, existing home set, and then 4 study homes in the new home set. A little bit. So yeah, so I think it's very encouraging from the occupant standpoint. I think it's very scalable for utilities. I think it's very encouraging from an HVAC contractor standpoint. I think that there's some HVAC contractors that I've talked with that are sort of on the fence of this new technology and not sure if they want to invest in training and the technology and their crews. And I think that it's very promising results. And then we continue to work with manufacturers to, I think, kind of fine tune the moisture management part of these systems, especially in the humid, mixed humid Southeast. And then we're hoping to excited for just more data from the new homes. I don't expect any sort of new aha moments or any new realization, but just sort of further reinforcement and further validation that the new homes systems are performing the way that they have in the past. So, but more to come on that. And then I think kind of, finally for some interesting takeaways, one of the things that I wanted to provide is this notion of, well, so how much sort of on these, I guess, new home, homes or new data from homes now, are the heating and cooling systems of homes still a high energy demand for a typical home? And so again, we only have data from an existing home. So this again is the Black Bear study home from the existing home sample set. So this is the home with the Mitsubishi system, and so this is the whole home, like looking at a winter day. In this case, it's January 22nd. So looking at one winter day and comparing the sub-metered HVAC portion of each hour to the whole home AMI data for each hour. How much does the HVAC system in blue consume compared to the whole home energy consumption for that hour in orange, again, for the winter time. So this is the winter day, and we can see kind of this interesting sort of signature where, especially sort of in the cold morning and cold winter morning, the HVAC system proportionally has a lot of consumes a lot of the energy for the home. And then later on in the afternoon, there's a lot of HVAC consumption compared to other parts of the home in the wintertime. And then likewise in the summertime. So in this case, in the summertime, we see, and this is sort of July 20th, we see again throughout each hour of a day, we see that in the summertime, there's actually sort of more base load, or there are other energy consuming devices or other things, non HVAC related that are adding to that that home's demand for that hour. And so it looks like in the wintertime, the HVAC system absolutely is still kind of the large consumer per hour of energy. But then in the summertime, it looks like in this specific case of this specific home, that the HVAC system is a smaller portion of the whole home consumption throughout the day. So with that, I'll kind of wrap up. I think kind of the full slide deck that I'll provide here probably tomorrow.
And one quick thing, Jonathan, if you don't mind, if you can stop sharing, I'll share one thing as the last teaser related to these two graphs. So let me see here. So that 98th percentile, oh, I'm sorry, you're seeing some of the breakup of here. Hopefully you're seeing a similar graph to what Jonathan was just saying. And just to round out for these new homes, we have the whole home AMI data for every day, every hour for the whole 2 years. This is each of the 4 homes on a December system peak day. You know, we can look at each one home like you just did, Jonathan, with the whole home. Now have the HVAC, so we can kind of see these evening peaks. Was that result of them coming home and, you know, kicking in, and they don't have strip heat? What happened there? But I think we can draw a lot from that and take one of these lines as one home, look at each home, so we could do the, or group them, the 2 Mitsubishi systems, and then the 2 Bosch systems, and, you know, run the outdoor air temperature by hour and the relative humidity against those graphs to kind of get at some of the points. Yes, we're going to have occupancy differences in the setting, but we can, if we're laying that over top of each other, we can actually see, well, when they're running the system like this, here's what the relative humidity looks like at these outdoor air conditioners, outdoor air conditions, both temperature and humidity, because the homes themselves are a lot more similar, being new construction type. So size wise and the construction level, you know, we can kind of take away some of the differences in the thermal envelopes that we would have in some of these existing homes. So that's some of the stuff we're teasing out, and just, you know, when does this the systems peak, but also the home peak? Because to make the point about the 98th percentile, as long as that 2% is not happening during our peak times, both you know, that's 3/4 of the battle right there.
Absolutely.
Just not to belabor the point. So yeah, thank you for letting me share briefly.
Yeah, great points.
Yep.
Question. I mean, you know, for the customer, as much as anything, the bottom line is, well, how much am I paying for heating or cooling?
Yes.
And you know, did you come up with just, okay, for each of these homes, what's the annual bill of just for the heating, just for the cooling for each of the homes, regardless of the monthly or you know, hourly consumption?
I'm glad you said that. We really had, that's something very easy to add on with both of these, so we could run that and say, here's the annual bill for the HVAC portion in the whole and for the rest of the home for these. That's something simple to visually. Thank you, Brad. Yes.
Yeah, actually, if I could quickly butt in, I think it would be really interesting to do, because Duke is actually guaranteeing the heating and cooling energy use for all 4 of these homes as part of their new construction rebate program. So it would be interesting to figure out what the heating and cooling bill was versus the guarantee that Duke is offering too. It would be interesting to see those side by side. And
we've got those since we guaranteed. Thank you for butting in, Amy, for that. I wouldn't even think of that for those. So we actually will run those ICF. I was going to say we do it all to begin with. We look at it both. Yeah, we're guaranteeing. So we can pull that fairly readily.
I was thinking that was going to be your last slide.
So I thought very interesting was that slide showing December, whatever it was.
Oh, hold on.
Versus the other. If you could go back, Jonathan, like 2 slides before your end, that was dramatic.
Somebody did a real extreme setback on their thermostat.
Yeah. Obviously, the behavior in these houses is just radically different. Yeah, go back 1 slide. And to the winter. Yeah, there you go. I mean, look what a percentage of that load HVAC is. That is wild.
And that looks similar to when we had somebody, they're different occupancy. I'm just saying for being with outdoor conditions was like a 23 and 56 degree day, you know, where it really pops up pretty warm real quick in the afternoon. We see those home loads just really drop until the evening. And some of that could be when we have the extreme range of temperatures on a winter day too. So.
Are you guys using that for like jet load control? I mean, for generation control, that you're looking at the weather and knowing this is going to change? Clearly. Yes. Yeah.
I was thinking these guys must have had solar panels.
Well, yeah, and so in particular for this study home, I mean, one of the things that this homeowner really enjoyed using their storm door on their front door, and so when I think it was maybe 100% of the time or 90% of the time when I went to this study home and went to collect the data, the front door was open and a leaky storm door was closed. And so here, I think from like a cross-selling measure or like an incremental fine tuning, it's like, I would be interested to be like, okay, well, how can we help replace your storm door with a better storm door? That would be a cheap thing, and try to see, is there any impact there on the heat loss or heat gain of the home?
What's hilarious is that JAG doesn't even install storm doors. So this homeowner likes that storm door so much that they bought it and installed it.
Oh,
like
sorry.
after the house was built.
Yeah. Sorry, Amy. This again is the existing home. So this.
Sorry.
Yep. Sorry, I didn't clarify that earlier, but yeah. But that's a great point with JAG. One of the things I think, Brad, one of my, I guess, big disappointment that I had, but I was hoping to see, I guess, sort of a more dramatic, what I would think of as normal performance of a 10 SEER system. I was hoping to see sort of more strip heat use and just kind of
more spikes.
Yeah, and so maybe more indoor thermostat settings to then see more spikes, to say like, okay, then now once we overlay that, or once we multiply that with 12 cents a kWh, then what's the 2-year energy performance? What's the cost of running the 10 SEER system compared to running the 17 SEER system? Because right now it's not going to pencil out to be very different because of, in my opinion, because of the set point temperatures.
But that house seemed to have a lot of zero values for the heating use in the lowest temperatures. I mean, do they have a wood stove or something in there? No. I mean,
they just liked it. They just liked it really cold, and they wore layers. So
that's where you almost have to analyze that with the differential temperature, because of course the house load, the load is a function of differential temperature, and so is the HVAC system load.
Yeah.
Complex because it has to do with temperature too.
Oh, sure.
But it's like you almost have to factor in both square footage to get it as an EUI kind of number and differential temperature, because the performance, the behavior in these things is so different. And the other thing Judy noticed was you were looking at the peak hours. Boy, I mean, that could really, it looked like there might be some really different timings in the home versus those peak hours. It looked like some of these people come home late, eat late, different people shower different times, that kind of stuff. So almost hard to sort of generalize based on those peak hours.
Yeah, right. Absolutely. And so then I think kind of a potential follow-up study would be like, could there be like a behavior-based incentive that could be beneficial to the occupant, could be beneficial to the utility. So great questions. And I think kind of like further unknowns and further interesting details for follow-ups.
I wanted to just say thank you for all the detail work you guys have done on this thing. It's really amazing. And I want to ask just a general question, like as a consumer, for example, there's a lot of housing being built in Asheville right now. I mean, a whole lot, and there's going to be more of it. So it's a good time for some opportunities what would Jonathan, you or Mark come up with if you had all the money now and you're Duke Energy and you're going to come up with a rebate program and you want to put in the most efficient thing or incent the most efficient thing, and from what you've learned in the study, where would you put your money to have people buy what? Duct, ductless, high SEER, no strips? What would you do to really make a difference in what we're trying to do, renewable energy, climate, and everything else? Where would you put your money to tell people to get what?
I would, go ahead, Mark.
Then I'll jump in.
So I would say, yeah, from Jonathan with Advanced Energy or just personally, professionally, I mean, I continue to be impressed with all of the high SEER, high efficiency systems. And so I think that there are a variety of brands. I think that there are a variety of models. And so I think whatever resonates, whatever applies or matches the occupants' desired outcomes. And so some of them may not want something hanging on the wall. Some of them may be okay with something hanging on the wall. And so I think that, yeah, my first recommendation would be, to encourage a load calculation based on the current conditions of whatever house, a new home, existing home, but to do a load calculation and then size that variable capacity system to that load, and whatever brand, whatever model it is.
Yeah, and Bill, since you add so much to the question, that's a broad question for new construction. We have existing, but new, there's an opportunity. So what are we investing in infrastructure? Is it, depending on the home, there's I'm going to push the heat pump water here, Bill. But yeah, that or even some storage or even solar thermal along with some PV in there. There could be, community type things for storage, and with new construction, you got a new development, maybe opportunities for that community geo type thing as well, depending on the lay of the land. So I think it really needs to be wrapped up as a new construction design type incentive, just thinking long term. To your point, the whole, not just the house, but that new development as a system, moving more towards being able to distributed generation with the right mix of whatever we have in there, renewable. So it may involve some variable capacity systems or some type of larger storage fields.
Thank you.
I think one other sort of kind of last comment is on that. I think that, yeah, I think that HVAC system, a variable capacity or high efficiency HVAC system, I think I have a growing concern of moisture management, especially in our climate. And so I think that because of codes, because there are a lot of kind of building codes that are adopting higher insulation levels, higher tightness levels. And so meanwhile, the moisture, the outdoor moisture is sort of staying at least in our state, is kind of still staying around. And so I think that as homes get tighter and more insulated, that from a comfort standpoint and from a durability standpoint, like having a moisture management strategy that also, oh, by the way, it provides heating and cooling. And oh, by the way, it provides sort of favorable energy coincident with the utility peak. And oh, by the way, it's quiet. And so these other benefits, I think, kind of for me, if there was sort of, again, sort of one recommendation, those are some of the.
Yeah, I mean, I would jump in and say that was a surprising thing for me in the study. I thought that the moisture management would be better. And I know that with the new homes, we were pushing the envelope on the rules. Like, I think most of them came in just under the wire of where a manual S says you're allowed to size it. So they were max. But I felt with the variable speed that we would still get pretty good moisture control. And it was, none of them were great, although only one of them was really kind of in what I would consider the danger zone. I mean, I don't know how easy it is to get to that graph, but you know, like you really want to be on, you tell people you want to be under 60%, but in reality, that's just because you really need to be under 70%, and 60 is 10 less than 70. And I'm not sure how accurate these sensors are anyway. So like the mouse is, you know, I'm not thrilled with, but the other ones, you know, are probably okay. But that is also an hourly average return. It would be, I'd kind of like to see a scatter plot of it, because, you know, I don't want, if it's 50 sometimes and 80 sometimes, that's not great. You know, I don't want to be at 80 ever. So, and, you know, I guess in Asheville, since one of these houses was mine, and I have a humidity sensor on my fridge, and I felt like I was getting better humidity control than this study showed I was. So I'm kind of convinced that in my house, a lot of my high humidity readings happen when my windows are open, like today. Because I just like, I don't see it when I check it, which is usually when my AC is on. So there might be more to what we're seeing, but in general, I was disappointed and surprised by that. And I don't know, it'd be good to maybe get feedback. You know, if that's a real effect that's happening when AC is running, we probably ought to be pushing more homeowners toward like a dehumidifier ventilator in this climate. But is that something that Duke can find a way to incent, since it's not an energy savings measure? It's more of a health and durability measure.
This could also be, though, a setup function, because if you have the fan speed too high, I did notice that you said where the returns were. That was very good, Jonathan. Where the returns were, it looked like just offhand that there were some high returns, which is the important thing for cooling. And in that case, having the fan speed lower for the summer, because you could do separate fan speeds usually on these systems for winter and summer cooling and heating. The fan speed lower on cooling would control humidity better and would in fact result in a lot less energy used as well. So, and you know, they could easily be people just setting a moist to high on cooling when they're installed, and that would not be the best for the home. Lower fan speed, more dehumidification, lower humidity, you don't have to cool the house as much because it feels cooler. And so that could be a whole thing that could, a training thing right there. That would be an interesting result to pull out of this.
Yeah, and so specifically
for these houses.
Sorry, what was that, Amy?
That would be a good data point to get for these houses. What was the fan speed?
Yeah, and so, yeah, that would. And so for, in this slide, again, the Beaver study home is the 10 SEER sort of baseline heat pump. We didn't open up the air handler or put a transverse the duct, return duct to get a fan speed on that. But so the orange Black Bear, that's the variable speed Mitsubishi system. And so that one would vary depending on the demand and the capacity and then the band of set point. And then the gray Copperhead, that's Amy's geothermal system there. I would add too, from a moisture standpoint, I'm not totally surprised at the high readings for, so the Beaver and the Black Bear study homes, they had visual, I could see visual holes in the ductwork in the vented crawl space, and I could see visual holes in the building envelope. And so I would say that the Beaver and the Black Bear in particular were sort of, I mean, probably classic, average 30-year-old quality construction. And so I think too, from a potential cross-selling of measures for utility having a program. I mean, I think it's great that the Smart Saver program has duct sealing option incentive, and they have HVAC upgrade incentive, and then they have a heat pump water heater incentive. They have added insulation incentive, and so I think that in this case, we didn't do any duct sealing of the Beaver study home or the Black Bear. We didn't do any air sealing, home air sealing. And because we wanted to get a representation of what is a typical a home condition could be. So
I go back to that Beaver though, because I remember there's another graph a little further back that shows the outdoor air temperature versus usage of scatter plot. And there were so many zeros on it. I just go, well, what is going on there? Were they using maybe space heaters, for example? My father and mother used to do this. They use space heaters. One back, going. I'm thinking, oh, well, that's much more efficient, but they're electric strip. They're just only in the room where you're in, There you go. I mean, now keep going. I think
so were you thinking summertime or wintertime?
it was winter.
Winter, okay.
And it was the whole winter. It wasn't the specific hours. One more, a couple more.
Oh.
Is that it?
Yeah, so it's this or
Look at all those zeros on the Black Bear, I guess it is. Go back. There you go. Look at all those zeros down there between 20 and 30. I mean, it's like, I don't know. I just gotta look at that and go, huh? Really? I'm not sure I believe that. I just gotta go, you're doing something else. You're sort of fudging that you're fooling the data collection is what you're doing, because there's something missing.
That could also be a night setback thermostat, because there are those hours when it drifts down. In my house where that happens, mine's the gray. I would almost guarantee you those are passive solar times, because you get good passive solar sometimes when it's really cold and clear outside. So there are definitely times when it's below 30 degrees when my house is hot. But yeah, it could be a night setback thermostat for the Black Bear.
mm-hmm.
Amazingly how tricky, when you really get real data sets, it is.
I think you probably need about 100 or 1,000 homes to really draw complete conclusions because of just what we're looking at.
Oh, even then, there's always some reason why there was just too much variation in the 1,000 homes or something. Data's tricky.
And I'm wondering about this geothermal system, if maybe there's like a fan using a lot of energy, or there's some constricted duct dampers that aren't, with something. I just kind of look at that number and go, wow, why is that geothermal system so high relative to what I would think it was? Although the peaks were not.
In the winter or the summer?
In the winter or the summer?
I'd have to go back and pull through the graph. I really remember, I kept noticing how the Copperhead was like, it's a home office, okay? So that's a completely different thing. But it did seem like there's a lot of constant energy use there, and it just seemed higher than I would have thought.
So Rick, one thing to know about that system,
yeah, there you go.
From about roughly the 1st of December to the end of February, and I would email Jonathan when I did this, I would switch it to radiant floor. So that system can do forced air heating, or it can do radiant floor heating. So when it's on radiant floor, there's no fan energy, but it actually does, the listed efficiency of it is actually a little lower when it's on radiant floor, because if you look at the listed efficiency, it's a 2-stage system, and the listed efficiency is much higher for the low stage than the high stage. And it says that it should run in the low stage most of the time. If you're forced air heating, especially since I run the forced air when it's milder out. So I should be getting really high efficiencies in the forced air. In the radiant floor, it only runs at like high speed. So it is less efficient actually to make radiant floor, but you don't have the fan energy. And I have never been able to, I don't have granular enough data to analyze what the trade-off between geothermal efficiency and fan energy is. So, but just like be aware of that. Like the colder it is outside, I'm usually using radiant floor.
Yeah, and so then I think, as you mentioned, like in this chart, in this color-coded chart, these taller belts that are closer to the 3 kW over an hour, those are kind of more indicative of those more classic, like December, January, February months.
Yeah.
That may kind of align with the radiant floor.
So Jonathan, I just sent you my model number, but you can look at like the catalog data for what it does in forced error radiant.
Okay, perfect. Thank you.
Regardless, amazingly stable though. Looks more like an industrial load than a residential.
I know, like that part of it I think is super cool.
Yeah.
Yeah, and talk about predictable peaks or predictable load.
Yeah.
That's quite predictable.
Yeah, that's what.
Is there any opportunity to go back to Beaver and Black Bear and perhaps weatherize them and then continue collecting data?
Yeah, I think that's certainly an option. I mean, we're open to funding sources. I mean, I specifically mentioned to each of them the Blue Horizons project, that it's like, hey, there's a great local resource to further sort of dial in. But yeah, I mean, they were each very very interested and engaged in the study and very helpful and appreciative. And so I feel like that if we were to propose that idea, that they would be more than open to kind of a follow-up.
I guess on that as well, you mentioned it in part, just sort of in general, the design construction of the old versus new, obviously with one very unique outlier. What would you say, sort of, again, envelope, again, you mentioned being able to actually see holes in the envelopes, window vintage, guesses on insulation, thermal mass in the different buildings. I'm just trying to get a feel for, I mean, it seems like a lot of the occupant behavior, especially if they're, running in the low 60s, has a lot to do with it, but I'm just kind of trying to do a sensitivity analysis in my head.
Yeah, I would say, I thought that I may have had some pictures of the outside. Maybe I don't. Yeah, so these existing homes, I mean, all of them are light framed, site built, 2x, studs. I'm not sure that if Amy has 2x6s, but I would assume that the Black Bear and the Beaver study home, that they are 2x4s, 16 on center. And then, so yeah, I think kind of a 1980s construction. They're a townhome. It's a townhome sort of development. And so I would imagine that there's very sort of similar construction between the units. So there's one, so the Beaver study home is an end unit. So in terms of like exposure to temperature difference, there are 3 walls for the Beaver study home. There are only 2 exposed walls for the Black Bear because it's an interior townhome unit. But same floor plan, same layout, same duct system, and yeah, sort of a 2-story home, single zone, but you have the duct, the air handlers in the crawl space. So the Black Bear study home, I was able, there was an attic access for the Black Bear study home. There was not an attic access cut in for the Beaver study home, because we had Advanced Energy had sort of talked internally about wanting to, whether or not we should do some intentional duct sealing. And if we were to do some sort of pre-study duct sealing, we'd want to make that consistent between the two participants. And so we didn't want to have to cut in and create an attic access to the Beaver study home that didn't have an attic access, whereas the Black Bear study home did. Yeah, I mean, I would say that the ceiling insulation in the Black Bear was, I mean, typical sort of mountainous, where many spots were very sparse, very thinly covering the sheetrock ceiling, couple inches of blown insulation, blown fiberglass, to other areas that were mounded up, sort of maybe 6 inches, 8 inches at the most of mounded blown fiberglass in that ceiling. I mean, I would have guessed probably R4 insulation for the ducts. And then there was floor insulation for each of those existing homes, and that again was kind of the classic R19 insulation, but the tiger teeth or the metal had fallen down so much that you can look. There's an airspace between the craft facing and the bottom of the subfloor, so it was pretty much not doing anything except just filtering the air. So from a performance standpoint, there was really no floor insulation performance-wise connected to a vented crawl space. And yeah, I think a lot of area of opportunity. And so I guess anecdotally, I was frustrated that the HVAC contractor, so I was there during the HVAC install for the Black Bear, sort of kind of the intervention or the newer system. And I engaged with the HVAC installer to see how they chose the size of that system as a replacement. And they said that they upsized it just to be sure that it was going to work. And so the old system for the Black Bear, and again, the Black Bear is an interior unit, and the old system was a similar 2-ton system as the Beaver, study home, which has 3 exposed walls. So 2-ton for the Beaver study home. There was formerly a 2-ton for the Black Bear study home, replaced with a 2.5-ton variable capacity system. And so, yeah, I was very much disappointed that the HVAC contractor chose to install a 2.5-ton system. And so then now it's, for me, an additional sort of frustration is that if and when that home then gets retrofitted, then that system is then going to be even further oversized for the sort of post retrofit condition of that home. So I tried to engage the HVAC contractor early and often to try to encourage a load calculation and try to help and to more appropriately size the brand new variable capacity system. Instead of a 2.5, go with a 2-ton, but it didn't work out. And so that's sometimes what we experience in the field. And so this is very much kind of a reinforcement of some of the other real world situations that we experience.
That brings up a really good point that I don't know why I hadn't considered it, but at least with these variable systems, folks aren't doing their retrofits in the right order. Then at least you have a little bit more buffer for hopefully someday when they go in and properly retrofit the space.
Yeah, and then likewise, I think it's great when a utility has incentive packages that also kind of encourage multiple retrofit measures at once, so that again the clients and the customers and the occupants have that opportunity, or maybe encouraged to buy multiple measures and to afford multiple measures based on potentially more rebates or more incentives to maximize their current budget and maximize their current selection, and then also potential future measures that they may do later on as the budget allows.
Yeah, and really anything that the utility ever gives rebate on for an HVAC system should require a copy of the Manual J.
Here, here.
Manual J is required by the board. I mean, it's not like we get, you're required to do this. It's not like you're asking an additional load for anyone. It's a flat out requirement. You can get cited by the board for not doing it.
Yeah, and we're right there with you, encouraging and doing what we can to support and provide incremental education so that those HVAC contractors comply with that and are accurate with their inputs and outputs. Yeah, I totally agree. Well, yeah, well, thanks again for great questions, engaging conversations. Again, I'm happy to provide a copy of the slide deck. Yeah, we're available to answer more questions. Certainly want to share our findings with the new home study. Whenever those come out, we're happy to pass that on. But yeah, in the shorter term, I'll sending over a PDF copy of the slide deck so that we can email it kind of fairly easily.
Yeah, this has been great. Thanks so much. I'm sorry we kept you a little over, but it felt like folks were really enjoying it. So I'm going to try really hard not to crush and let it sort of wrap up. But again, thank you so much, and we look forward.
Yeah, thank you for the opportunity. I appreciate it.
Thank you.